When installing a 400 amp 208/120 volt Y panel, determining whether to count the neutral as a current carrying conductor is crucial for safety and code compliance. In this scenario, the neutral must be considered a current carrying conductor for two primary reasons. Firstly, the panel is a 400 amp service which exceeds the 225 amp limit specified in the National Electrical Code, or NEC, for not counting the neutral per 310.15. Secondly, the calculated load of 263 amps surpasses the 200 amp threshold, further necessitating that the neutral be accounted for as a current carrying conductor. The nature of the load, particularly the presence of fluorescent lighting, introduces another layer of complexity. Fluorescent lighting is classified as a nonlinear load. Nonlinear loads draw current in a non-sinusoidal waveform, which generates harmonics that can distort the voltage. These harmonics significantly impact the neutral conductor, potentially causing it to carry more current than anticipated. Given that the fluorescent lighting accounts for approximately 100 amps of the total 263 amp load, it represents a substantial portion. According to 310.15, when the major portion of the load consists of nonlinear loads, the neutral conductor must be derated to 70% of its ampacity. This derating is essential to prevent overheating and ensure the safety of the electrical system. For a 400 amp panel, the neutral busbar is initially rated for 400 amps. However, because the fluorescent lighting constitutes a significant nonlinear load, the neutral ampacity must be derated. To calculate the derated ampacity, multiply the original ampacity by 0.7, reflecting the 70% derating factor. The calculation is as follows: neutral conductor ampacity equals 400 amps multiplied by 0.7, which equals 280 amps. Therefore, the neutral busbar must be derated to 280 amps to comply with the NEC guidelines and ensure safe operation. In summary, it is imperative to count the neutral as a current carrying conductor in this installation. Additionally, because the fluorescent lighting contributes a substantial portion of the nonlinear load, the neutral busbar must be derated to 280 amps. This derating ensures that the neutral conductor can safely handle the harmonic currents generated by the nonlinear loads, maintaining the integrity and safety of the electrical system. Understanding the NEC requirements for neutral conductor derating is critical for any electrical installation, especially when dealing with significant nonlinear loads such as fluorescent lighting. Correctly applying these principles ensures compliance with electrical codes and enhances the safety and reliability of the electrical system. Failing to account for the neutral conductor and derate it accordingly can lead to several potential hazards. Overheating of the neutral conductor is a primary concern. When the neutral carries more current than it is rated for, the conductor's temperature increases. Excessive heat can degrade the insulation, leading to insulation breakdown and potential short circuits. This, in turn, can create a fire hazard, endangering the building and its occupants. Additionally, harmonic currents can interfere with sensitive electronic equipment. Harmonics distort the voltage waveform, which can cause malfunctions in electronic devices such as computers, control systems, and other sensitive equipment. This interference can lead to data loss, equipment failure, and costly downtime. Moreover, failing to comply with electrical codes can result in legal and financial consequences. Electrical inspections are conducted to ensure that installations meet the required safety standards. If an installation is found to be non-compliant, it can result in fines, mandatory corrections, and even the shutdown of the electrical system until the issues are resolved. This can lead to significant financial losses and operational disruptions. To ensure compliance and safety, it is important to follow a systematic approach to neutral conductor derating. Firstly, accurately calculate the total load. Determine the total amperage of all loads connected to the panel, including lighting, equipment, and other devices. Secondly, identify nonlinear loads. Determine which loads are nonlinear and estimate their contribution to the total load. Common nonlinear loads include fluorescent lighting, electronic ballast, variable frequency drives, and electronic power supplies. Thirdly, determine if the nonlinear load is a major portion. Assess whether the nonlinear load constitutes a major portion of the total load. According to 310.15, if the major portion of the load is nonlinear, the neutral conductor must be derated. This determination often requires engineering judgment and a thorough understanding of the specific application. Fourthly, calculate the derated ampacity. If derating is required, calculate the derated ampacity of the neutral conductor using the appropriate derating factor. For example, if the neutral conductor must be derated to 70% of its original ampacity, multiply the original ampacity by 0.7. Fifthly, select the appropriate conductor size. Choose a neutral conductor size that is capable of handling the derated ampacity. Refer to the NEC tables to determine the appropriate conductor size based on the ampacity and other factors such as temperature rating and installation conditions. Sixthly, ensure proper installation. Install the neutral conductor according to the NEC guidelines, ensuring proper connections and terminations. Proper installation is critical to ensure that the conductor can safely carry the current and maintain its integrity over time. Seventhly, verify compliance with local codes. Check with the local electrical inspector to ensure that the installation complies with all applicable codes and regulations. Local codes may have additional requirements or variations that must be considered. Additionally, consider the use of mitigation techniques to reduce harmonic currents. Harmonic filters can be installed to reduce the amount of harmonic current flowing in the neutral conductor. These filters can improve the power quality and reduce the need for derating. Also, consider the use of phase cancellation techniques. Phase cancellation involves balancing the loads and the three phases of the electrical system to minimize the neutral current. By distributing the loads evenly, the harmonic currents in the neutral conductor can be reduced. Furthermore, consider the use of energy-efficient lighting. Energy-efficient lighting, such as LED lighting, typically produces fewer harmonics than traditional fluorescent lighting. By switching to energy-efficient lighting, the amount of nonlinear load can be reduced, potentially eliminating the need for derating. Remember that the NEC provides specific guidelines for derating neutral conductors. These guidelines are intended to ensure the safety and reliability of electrical systems. Ignoring these guidelines can lead to hazardous conditions and code violations. So, always consult the latest version of the NEC NSEEK guidance from qualified electrical professionals. Proper neutral conductor derating is an essential aspect of electrical design and installation. By understanding the principles and following the NEC guidelines, you can ensure that your electrical system is safe, reliable, and compliant with all applicable codes and regulations. In the context of installing a 400 amp 208/120 volt Y panel in a dollar store, the presence of fluorescent lighting as a significant portion of the load necessitates careful consideration of neutral conductor derating. Firstly, verify that the fluorescent lighting is indeed the major portion of the load. Calculate the total connected load, including lighting, HVAC systems, refrigeration equipment, and other electrical devices. Determine the percentage of the total load that is attributed to fluorescent lighting. If the fluorescent lighting constitutes more than 50% of the total load, it is generally considered a major portion. Secondly, assess the harmonic content of the fluorescent lighting. Fluorescent lighting typically produces significant harmonic currents, particularly third harmonic currents. These harmonic currents add directly to the neutral conductor, increasing the neutral current. Use a harmonic analyzer to measure the harmonic content of the fluorescent lighting. This will provide a more accurate assessment of the impact on the neutral conductor. Thirdly, consult with the lighting manufacturer. Obtain information from the lighting manufacturer regarding the harmonic content and characteristics of the fluorescent lighting. The manufacturer may be able to provide data or recommendations regarding neutral conductor derating. Fourthly, consider the use of harmonic mitigation techniques. If the harmonic content of the fluorescent lighting is high, consider using harmonic filters or other mitigation techniques to reduce the harmonic currents in the neutral conductor. This can help to reduce the need for derating. Fifthly, consult with a qualified electrical engineer. Seek guidance from a qualified electrical engineer who has experience in electrical design and harmonic analysis. The engineer can provide a thorough assessment of the specific installation and recommend appropriate derating measures. Sixthly, document all calculations and decisions. Keep a detailed record of all calculations, measurements, and decisions related to neutral conductor derating. This documentation will be valuable for future reference and for demonstrating compliance with electrical codes. Remember that neutral conductor derating is a critical safety issue. Improper derating can lead to overheating, insulation breakdown, and potential fire hazards. So, always take a conservative approach and prioritize safety when making decisions about neutral conductor derating.